Hello, everyone, and welcome to this Ignion webinar. My name is Katie, and I will be your Global Spec moderator today. And yes, you are just hearing my voice. Now I'm going to pass things over to our Ignion moderator, Karen Soriano. So Karen, welcome to today's event, and I'm going to pass things over to you to get started.
So thank you so much, Katie, and also welcome to everyone who's joining us today. So today's webinar is all about why antenna designs fail in the real world. So today we'll unpack why those pretty plots fall apart once, we have enclosures, batteries, real world constraints enter the picture. Before we dive in, allow me to introduce our today's speakers. So first up, we have Katerina Galitskaya. She's a senior antenna engineer with over a decade of experience spanning IoT, wearables, and even base station antenna design. Katerina is also an active voice in the EM simulation community. You might recognize her from her technical blog in the Microwave Journal or her weekly RF deep dives. So Katerina, perhaps you want to say hello to our audience, especially those who are following you on LinkedIn.
Hello, everybody. I'm really glad that you joined us.
Thank you. And joining her is Sifiso Gambahaya. So born in Zimbabwe and raised in the US and India, Sifiso brings more than 20 years of global experience designing, testing, and manufacturing RF solutions for commercial and military applications. He's held engineering roles at Ericsson, CommScope, and Corvo, and has led antenna development projects in South Africa, China, Taiwan, the UK, the US, and now here in Spain as Director of Engineering at Ignion. So maybe, Sifiso, you want to say hello to our audience also? I think you're muted. Can you check your microphone? Hello? Hello?
Sorry about that. I was on mute. Hi, everybody. Yep. Looking forward to interacting with y'all.
All right. And as Katie said, my name is Karen Soriano. I'm the Product Marketing Manager here at Ignion, and I will be moderating today's session. So first, let's look at what we're going to be covering for today. We'll dive into real-world failure modes. So these are the common mistakes that cause antennas to look great on paper, but then fail in the field. Then we'll break down the top 5 must-follow integration practices. After that, we'll take a quick poll, and then we'll have a short Auxion demo. So Sifiso will show you how this platform flags integration risks and predicts antenna performance before you even build a prototype. And finally, we'll open the floor for your questions. We have received some in advance, and we'll try to answer as many of the live questions as we can. So let's get started with some common antenna integration errors and case samples. So here's a classic one, antenna placement. So Katerina, Sifiso, when you review antenna designs, how often do you see antennas placed in like suboptimal positions? Maybe let's start with you, Katerina.
Yeah, it's very often. It's one of the most popular problem, I would say, that antenna kind of entering the project that's very late stage, right? So when we already have not so much place on the PCB, we have only like some real bad real estate left on the PCB, and we just think, okay, we will put antenna there and it will be okay. But it will not actually. Antenna depends a lot on different things, especially on the position, on the surrounding, on the environment. So we really need to think about antenna first. It's always been kind of like surprising for me when you design a wireless project, right? A wireless device. One would think that you would think about wireless part first, right? But
exactly.
Usually, but somehow this wireless part, like the most important part in wireless device, it somehow comes last in many projects. I've worked with customer electronics a lot, and I fixed a lot of this, like exactly these projects.
And Sifiso, from what is shown on these slides, what exactly went wrong in these layouts, and what would be their impact?
Yeah, sure. And I can't, agree more with Katerina, right? Because, oftentimes, product integrators, look at the antenna as, just a small subsystem of the entire system, from a cost perspective and also, just generally from a design perspective, right? But the reality is without comms, your product is virtually useless, right? So here we are, we got these pictures, it's illustrating some of the pitfalls of poor design or, thinking about the antenna at the last minute. So the rule of thumb always for us is put the antenna first, right? And then design everything else around the antenna. It's a lot easier in that way to fix any other problems you could have as far as performance is concerned, because the antenna is a sensitive device, right? So anything that surrounds it impacts its performance. If you look at the picture, the most obvious one is the one on the right. So here, you've got an antenna integrated on a module. And on top of that, it's sitting on top of a motherboard. And obviously there's not enough clearance for that antenna. So it's sitting on a ground plane essentially. And that's a huge capacitance that's going to kill your antenna radiation immediately. So this sort of integration is not advisable, right? So you want to create some clearance or distance. If you could elevate that motherboard, away from, the antenna, module, if you like, you could create that sort of distance that's required for performance. And this is obviously like a retrofit, because typically, what you're looking at here is an already certified module. And what you want to do is just plug and play with the bottom motherboard. But, these quick fixes don't always work, right? And if you look at the middle board, again, there's a footprint for the antenna, sitting on the top right. And you've got some sort of transmission line going down to some, ground plane. And obviously, the ground plane is not sufficient for starters for this sort of application. This was actually a cellular application. And also the location of the antenna is incorrect. In fact, you want to mount that antenna at the top of the ground along the width of the antenna. And, preferably, you have most of the ground plane with copper field, for proper RF performance, right? And then the picture on the left, this is more like a clearance, issue, where you don't have sufficient clearance and there's interference between the antenna and the adjacent ground plane. So these are all like, very important details that affect antenna performance and degrade your product, severely, and, you're not able to go to market.
All right, let's head to the next one. So you mentioned already about clearance areas. So Katerina, why is this such a common mistake? I mean, even among experienced engineers or experienced teams.
Yeah, I mean, it's kind of understandable because we tend to have smaller and smaller devices nowadays, right? We don't really have place. So we can okay, in data sheet, it says that it needs 5 mm clearance, but I have 3 mm. It will do. People tend to think like that because we want to have the smaller possible device, right? And we want to maybe feed more battery space there or something, more components or something like that, and the antenna will get less space. So that, I think that's why it happens.
And Sifiso, what, in your opinion, why does this keep on happening? And perhaps you can also walk us through this slide like what you did in the previous one.
Yeah, sure. Just like Katerina mentioned, products are getting smaller and the demands for performance are, getting exponentially higher. And, these are opposing effects, obviously. But if you have to look at these pictures, if you look at the picture, the second picture from the left, you can see an antenna footprint. You've got your transmission line and matching network, designed into the PCB. But if you look at the red triangle, the first red triangle, you can see some traces that are, in your keep out area. Those little traces are going to impact performance. In fact, they should not be there. All traces and any other, metal components should lie on the ground plane, on the PCB itself, not in the clearance area. And likewise, those, smaller squares also illustrate, more metallic components and traces that are in the vicinity of the antenna. So that's a no-no. Immediately, you're going to suffer greatly for performance. So yeah, we get it. Sometimes, our, typical customers, will talk about, well, I didn't have enough space. Or, some of the designs are an afterthought. It could be something like an LED, that needs to basically, light up. And an obvious place to place it is in that keep out area. But, that LED leads, they do have some traces, copper, essentially influencing performance, right? So these are things to look out for. And the rest of the pictures are just pretty obvious. There's not enough room for the antenna to breathe. There are rules regarding what you do for keep out, areas and so forth. And typically in any data sheet, we would stipulate those for a reason, because we've done some studies to understand, the impact of proper clearances, et cetera. The one on the left, that's a blatant mistake, obviously, because, in the design of this meandered PIFA, the long arm is shorted to the ground plane, right? So of course that's going to basically impact performance. If you get radiation at all from this, it would be a miracle. So yeah, it happens. That's what customers do from time to time. But there is an impact to this sort of like mistakes in design.
All right. Actually, the next slide is also all about big metal components. So I guess, but before we go through this one, I'm just thinking, when they design the device, they know that it's going to be small. But why does it usually change from the design to the actual device? And when you change, do you test, is it common practice to test it again? I guess, Katerina, you can take it.
Yeah, of course. So if you change anything, especially in the size, like especially in the size of PCB or like antenna placement, like you want to turn it or like put some, like, for example, here, battery close to antenna, that must be tested. Ideally in the simulation. So if you have, like, if you simulated before, like in some full wave simulator, ideally, or like if you have your prototype, if you can in lab test that, also can do. But just assume that it will work. Probably it will not work as you think.
And Sifiso?
Indeed, when you're designing, these antennas into your product, the first thing you want to do is confirm performance, with us, via simulation, for instance, right? And just ensure that, any metal components are as far away from the antenna as possible. And in fact, there are rules to that, right? And you need to follow those rules according to design guidelines. And, you could always, test your device, passively for impedance and, get some decent performance, so to speak. But oftentimes, when you have wires sticking out, those also affect the active performance, because, you have to worry about radiated disperse emissions, as an example, that impact your receiver sensitivity directly. So it's important to keep out anything, that could impact antenna performance, away from the antenna.
All right. Let's get to the next one. So these are actually some sample plots, I guess. Katerina, can you walk us through what's happening on this slide?
Yeah, and I also noticed that we got exactly the question already from our audience, exactly about this, that they have a PCB smaller than in reference, in data sheet that they use, right? So what do you do? And in this slide, exactly about this, that what you see when you have like your antenna and you have data sheet and it shows usually good, like some good performances. We can see here like 70, 60%, like in different frequency bands. And then, but they always in the datasheet, they say that we tested it on this reference board with this size. For example, here, 130 millimeters, 60 millimeters in width. And this antenna will only show this efficiency in these S parameters only on this reference board. If you have smaller, if you have bigger, well, bigger is not so dramatic, but smaller, if you have like wider, if you place your antenna in different place than they placed in the reference board, that will all show different figures. And like what you can do, of course, I understand that you cannot always have this optimal length of the PCB, right? Optimal position. You always need to tune your antenna in your environment. So usually each antenna, they have some matching network, right? So at least you can work with that. You can tune this antenna on your PCB and maybe even like think about that before. And if you have only like 2 components in matching network, maybe think about adding like more like pi network or even like 4 components, just in case you would need it to match your antenna better. Because you always can just leave this place, right, component place without the component and just kind of have a trace there. But if you don't have the place for the component, you cannot use it so easily. So yeah, we can maybe fine-tune the antenna better if you have different places. But this is very good to think about that, because your antenna will not work as in reference if you have different sizes.
All right. Now let's dig into a real Auxion layout example for an NB IoT tracker. So Sifiso, how sensitive are designs like this to what may seem like non-RF changes, like rerouting a trace or shifting the copper zone? And perhaps you can also walk us through the next couple of slides about this NB IoT tracker.
Yeah, sure. So this example right here shows you an NB IoT tracker design. And this was actually designed in our AI platform, which is Auxion. And essentially, it shows you 2 components from Ignion, one for, cellular and another for, GNSS. And the idea here is that, you want to design for performance, and the ground plane does matter. So that's the first thing. And as you start reducing the ground plane size, performance will degrade accordingly, right? So this is an example of, a co-design where you have, cellular and GNSS coexistence. And for that particular board size, you can see the efficiency, typically sitting at about 20% at low band and about 60, 70%, at high band. And you can expect performance to drop, obviously once you decrease the ground plane size. And mind you, this is a base design, right? So which means, you're looking at a bare board. So this is probably the best, kind of case, from a simulation point of view. But once you start populating your PCB, with components and do a proper layer stack up, design full layer or 6-layer, 8-layer, whatever the case might be, your grounding needs to be just right. You need to have the correct number of vias, for instance, to have a continuous ground plane, RF ground plane, to retain, performance to the same levels. Now, if you're looking at component placement, the same rules still apply. You don't want big metal, next to your keep out area, as an example, because that's going to degrade performance. One of our rule of thumbs is, any component that's taller than 8 millimeters or more should not be, next to the keep out area, because that's going to affect performance, as an example. And again, this is a clean board, meaning it's continuous. But typically, customers, are going to have all kinds of holes, or maybe even want to do split grounding, which we don't recommend, as an example. And performance will decrease accordingly as well.
I think, Sifiso, you have some actual examples in the next couple of slides. I'm just going to go flip over to those. So, for example, this one with the first and the final design comparison.
Exactly. So this case right here, illustrates a design where you have 3 antennas, one for cellular, on the right side of the PCB in the first design picture. And then you've got a GNSS and a Wi-Fi antenna integrated on the same board. The idea, looks sensible in the sense of, you're going to place your antennas in the top part of the PCB, and then you have your ground plane at the bottom. But that's not how antennas work, right? If you're looking at embedded antennas, they depend on the ground plane for performance. And so, we had to basically do a re-layout of this to ensure that there's proper, RF, performance. And the first thing to do was to move the cellular antenna from the top right corner to the top of the PCB, as you can see on the right side in that picture, and then lay out our Wi-Fi and cellular antennas and GNSS antennas accordingly, so that they make use of the ground plane for performance. So the design on the left basically become the design on the right for proper performance. So there's adequate ground plane, but what you're not seeing here is obviously another layer of via stitching, across the entire layer stack up of the design to maintain proper impedance integrity, also for your transmission lines, because that's also another factor. If you look on the design on the left, you have some transmission line which is not basically obeying any of proper design rules. If you're designing the transmission line to go to the radio, you want a proper CPWG transmission line, and to work out the 50 ohm impedance of that transmission line correctly, in order not to have impedance mismatch, once you have integrated your matching network into the design. So all these considerations were taken care of on the design on the right, essentially.
I think there's another slide here with another layer. Maybe perhaps this is the other layer that you were mentioning earlier.
Exactly. So, here, we have a continuous ground plane. So what we have is on the second layer, we have the same ground plane in the final design, and, we make it as large as possible. Now, this could be a power plane, as an example. But the whole point is, you want a continuous, RF ground plane. As much grounding as you can get, will help the antenna perform.
And then there's also about the layer stack up. Perhaps a couple of tips on this one?
Yeah, sure. So, the layer stack up is important, basically, right? Because your PCB is essentially the carrier for, different signals. So the RF layer typically is on the top, and that's where you integrate, your RF components, and you're designing your transmission line, et cetera. But you also need to have a reference ground, right? In that design. So, you can have an RF layer, you have a power plane, you've got a signal layer, and then at the bottom, you can have another ground plane, layer. And it's important for you to define which one is the reference ground in order to design the 50 ohm transmission line correctly. Because if you don't reference it correctly, then, you're going to have an impedance mismatch. But not only that, you could have what we call ground plane current loops, which is essentially signal leakage, because what you're trying to do is create a low impedance path between your RF signal and the ground, essentially. So you have a proper return path for RF currents. So it's important to have a lot of considerations to your PCB design. And yeah, one of the points we do note there is, we don't, advocate for, split ground planes. You want to make sure, even if you have power and RF in different sections of your PCB, it's best that you keep it on the same, continuous ground plane, essentially, for performance, and also to avoid these current leakages, that cause radiated sparse emissions.
All right. So just to wrap up this section, thanks again, Sifiso. I just want to give a reminder for the audience. If you have any questions for our speakers, we've covered a lot in the first 20 minutes of this session. Please type them in the question panel. We will now proceed to the some must follow antenna integration practices. So we'll try to breeze through this part so we can jump into the questions. So first off, I think you've already mentioned this earlier, include enclosures, displays, batteries, connectors in your plan early. And there's a percentage here. Expect up to 15 to 30% detuning once real materials and interactions are factored in. So I guess, Katerina, Sifiso, do you agree with this estimated detuning percentage, or should it be more or should it be less? So let's start off with you, Katerina.
Yeah, I think this is quite good number. I mean, it's quite wide, so because there are a lot of things, right? We have some tolerances in the material, we have some production tolerances, we have some if we have our enclosure, it can be different, like material, maybe from one batch to another batch, and yeah, it's everything that affects antenna, as we already said several times. So I think this number is good. You kind of need to expect that maybe design your antenna have a bit broader band to cover on this uncertainty, but just be prepared that you probably will need to fine tune your antenna in the lab after, while you're prototyping.
How about you, Sifiso? What do you think?
Yeah, sure. And Katerina is right. And it all depends also on the application, right? Typically, maybe, you get detuning in the order of, lower percentages for, free space device deployments. But, if you were to deploy the device on a human or a handheld device, or, have a wearable, on a person, then, you could have, much higher detuning, obviously. And this happens because of absorption of radiation in different parts of the body, or different parts, could actually, have different effects. So yeah, so the range, is within reason.
All right. The second point here is even non-RF changes like moving a screw hole or rerouting power, it can shift resonance or match. So track every edit and recheck antenna performance. So realistically, Katerina or Sifiso, how do you recommend teams manage layout versions, at least in your experience, so to make sure that they're not carrying this silent detuning into their next version or into their next prototype?
I would recommend to really be in close contact if you have separate antenna engineer, or if you do this, be mindful about antenna always, that every change, almost every change in the device that you do will affect antenna at some degree. So if you even change something that you think maybe not so, maybe material of the enclosure, but one would think that it's kind of so far away and it's some plastic, it doesn't even matter, but it will matter. So kind of be mindful about your antenna throughout the whole design process.
How about you, Sifiso? Anything else that you want to give, maybe tips from your experience?
Yeah, no, absolutely. Of course, the rule of thumb for us is, antenna first in everything we do, right? So I would say from design inception, you want to lock antenna keep out zones as an example, right? And then, you say this is a no-go, and, that will minimize, any of these, resonance shifts or degradation in performance. And then version control, all version control changes need to be noted. And, once those changes have been made, you got to resimulate that PCB to make sure that, performance is within your expected, specifications, obviously. And then, you got to actually build it and test it and see if those design changes are, adequate for performance. But most importantly, just have some cross-functional sign-offs also with the design teams from the other departments, and, ensure, keep out enclosures, ground plane, and all those things are, recorded and well catered for, so there's no silent changes, right? And everybody's on the same page, essentially. And there's no exceptions to that.
All right. Now, the third point here, feed real-world S parameters into your matching network design. Avoid tuning and isolation. Optimize with layout and housing context tied together. So in your experience, do you see engineers treating matching as like a one-time fix instead of an iterative process? And also, what is the risk in terms of tuning and isolation?
I think that's well, at least in antenna. If we talk about antenna engineers, everybody like in this field know that matching is really like fine tuning, really important, and that is actually what kind of brings your antenna from simulation to real world, right? So kind of you tune your antenna to work like in the real world with the real environment, and of course, if you, for example, design antenna for wearable like that's supposed to be work on the body, you need to tune it on the body as well. So if you design your antenna that it will be like located on some like metal plate, for example, I don't know, you need to tune it like that. So space tuning will not be the same as like final environment, and it's very important to have this matching network that really help us to get antenna where we want it to do it in the final environment.
All right. I'm going to jump to the next one because so we can go to the next part of the webinar. So we have here design for a plus or minus 10% tolerance for component drift, PCB stack-up variance, or aging effects. If your matching only works on nominal, it's not robust. So Sifiso, maybe I'll ask this question to you because you mentioned we had a chat before about this 10% like allowance, right? So do you agree with this? And if not, how big should be the margin?
Well, it all depends, right? So I would say plus or minus 10% is a good start, but it all depends on the RF bandwidth that you're working with. Now, for narrowband use, you need a tighter, tolerance, basically, because, those frequencies can shift or drift quite easily, and you can be mismatched quite easily. So you want to make sure that your component tolerance, in other words, your Q, is pretty high. And, that way, you stay within the performance requirements that you want to adhere to. Now, if it's a broadband antenna, for instance, some of those shifts might not matter so much, right? So plus or minus 10% is a good figure. But if you are doing a GNSS antenna design, for instance, or single band Bluetooth, 2.4 and, gigahertz, for instance, you want about 1% to 5%, tolerances. And essentially, that boils down to the matching network components that you're using as an example. But just to circle back, I think the discussion we had earlier had more to do with, moving from simulation to a real life product. So we always have some sort of margin, if you're getting 40% efficiency, in a real life product, typically, once you've integrated all the plastics, the housing, the battery, and so forth, in free space, you're probably getting about 30%.
Right.
And this is due to parasitics on the board, right? Because at that point, you have a multi-layer design and you have a lot of interconnects, and also just the tolerances of the components themselves.
Okay, so just to close this off, well, I guess the tip here is basically take advantage of tools. We have, for example, Ignion. So quick question, I guess, for Katerina. If tools like this, like such as Ignion, can catch the issues early, what do you think is stopping teams from adopting digital validation sooner in their workflow?
I think that's from what I see kind of from my audience. Maybe it's basically usually people maybe don't trust tools so much, and maybe consider it a waste of time. But I think that actually modern tools, like I tried Ignion myself, and like there are also like some like really big like antenna simulation tools, right? That you can use like maybe for deeper simulations. They are very good, like, and they really help to save like on several prototype rounds, like to not kind of go to some like really long prototyping stages. You can eliminate some of that with the proper tools.
All right. So I just wanted to bring up a few like gems during my preparatory chats with Sifiso, and I wanted this to open this as a discussion. We don't need the slides or no charts. So Sifiso, some of the things that I picked up when you said on the bare board you can lose 10% inherently at low band. You also said like for multi-layer return paths and split grounds matter, it could be worse. And then for wearables, you already mentioned something about the effect of the body, simulation solver setup and phantoms matter. And the way you connect phase correction, ground play extension, these also matter. And lastly, you mentioned also that it's difficult to simulate and measure accurately. We have to iterate back and forth. We kind of covered some of these points, but I just wanted to put that on the table in case you wanted to add anything.
Yeah, sure. I completely agree with the Sifiso that when we do some simulations, even though we try to, for example, like when I do simulations, I go to like as detailed as possible, right? Of course, there is trade-off, like you don't want to spend too much time on simulation, you don't want to be too heavy, but you want to be detailed. But still, even in this detailed simulation, I know that this efficiency that I see, it will not be in real life, that I will lose some. And I need to be really mindful about that because if I need to pass some certifications, so for example, like for some operators, right, or some like safety certifications, I need to know that what I see, there will be some like like lower values in real life.
Yeah,
So?
that's right, Katerina. You know, I would agree with that 100%. And typically, where you have devices that are performing at low efficiencies, you know, especially for cellular, you know, where you simulate, you know, antenna design and you're getting about 20%, you already know that you're at the margin of performance. And yes, you're right. You know, carrier certification, PTCRB certification is a key requirement for some of these designs, obviously. And if you look at it from a dB perspective, 10% in a loss from 20% to 10%, you know, dB wise, right? That's more than 3 dB. That's like 50% roughly, you know, of efficiency that you're losing. So you know, you got to look at it from that perspective. If your antenna is already, you know, somewhere around 70-80% efficiency, you know, at low band, you know, you don't losing 10% in a real product, you know, is not going to affect certification as an example, right? But you care when the antenna is somewhere around 30% efficiency or so. You know, you got to look at that design a lot closer.
Yeah. You want to squeeze as much as possible when you still can change something, right? Because you need to kind of like be mindful about this, that there will be a difference in real life.
I guess that's where Abzion, I mentioned it earlier, Ignion's antenna integration platform may come in handy because before you even build your first prototype, you can at least see the antenna performance. Now, I'd like to ask help again from Katie if we could launch this short video. And then Sifiso, if you could walk us through this short demo so the audience can see how Abzion works in practice.
Yeah, all right, everyone. So this video will open up on your screen automatically. So I am pushing that out now. So video is playing. So Sifiso, feel free to chat over that video. It is now playing out to the audience.
Yes. So, you know, here we're running basically a virtual prototyping session with one of our antennas, which is a Run-M Extend. It's a cellular antenna, and it's roughly 120 by 60 millimeters in size, you know, covering a 24 to 960 megahertz at low band. So that's typically band 5 and band 8. And, you know, it's also covering 1700 to 2690 megahertz in frequency. And we're using, of course, this AI design tool basically to work out the prescribed antenna location, clearance area, you know, feed line routing, and to basically optimize the design to see what yields the best efficiency and bandwidth match. And, you know, once you've done the first stage, which is literally the proof of concept, and, you know, you generate the results, you know, from that, and it also generates step files, Gerber files, you know, for that design. You know, the next step then is to do a Gerber review of your design. And, we're able to do that. All you need to do is just upload, your Gerber file onto the platform. And as long as you're following the proper, design rules, you've got design rule checks, pretty much like any of your PCB design software would, Altium or whatever it is you use, then everything should be okay. And you can, output, your design and, off you go to manufacture. But if not, you're going to get some errors. But yes, the platform does walk you through, the various stages on how to do that. And, if there's something wrong with the design, there's some warnings, that pop up. And typically then you have to engage with, one of the Ignion engineers, who can then assist you in person to ensure that, you pass that stage, and then you can move on to the next design iteration, essentially.
All right. Thank you so much, Sifiso. So we have 15 minutes left, so we'll try to quickly jump to the Q&A now. So to kick things off, we'll start with a couple of advanced questions that we received earlier. So Sifiso will take the first one, and then we'll alternate that with some live questions coming in from the audience, which Katerina will jump in on. So the first one, so we received a question from Luis. When using a 7-element matching network, can you share any general thumb rules for adjusting component values? For example, to improve return loss in the low band, is it helpful to increase the ZX and decrease ZY? Or is it good to shift a good RL peak toward a higher frequency band? What adjustments typically help? So maybe Sifiso, you can start with this one.
Yeah, sure. So this is more a general question. Since it's pretty general like that, I would say, there's no simple rule to that, hard and fast rule to antenna matching necessarily. But I would say, obviously, increasing your L and C, meaning your inductance and capacitance, typically lowers the resonance, and decreasing those, whether it's in shunt or series, depending what matching network topology you have deployed on your PCB, that would shift the resonance to the right. For single band antennas, that's pretty easy to do, to be honest. You could even do that without the use of specialized tools. But for multi-band antennas, especially, cellular, where you got to match over a broadband, but in discrete, frequency bands, it gets a lot trickier. So we at Ignion, we use OptanyLab software, which automatically generates matching networks, for us as an example. But yeah, the rule is, if you're going to increase capacitance and inductance, you can resonate a lot lower, and vice versa.
All right. I think there's a question here, especially for Katerina. So I can.
I think I think you mean the one about
the space constrained electric device.
Yeah, space constrained on the lower frequencies. Yeah. Mm-hmm. That is, of course, it's all very complicated on lower frequencies because we want bigger. We want to have a big ground plane. And there was also one more question about the optimal size of ground plane on lower frequencies. And the rule of thumb is to have quarter wavelength of the in length for a ground plane. So you just go through your from your minimum frequency. So for example, if you design cellular antenna and your lowest frequency is 700 megahertz, you calculate wavelength for that frequency, and then you have quarter of that, and that is the length of ground plane, the optimal for that antenna. The antenna will perform the best for this ground plane. Usually it's about 130 millimeters or so for 700 megahertz, like 800 megahertz. It's good, if it's better, it's okay. If it's smaller, then you start getting problems. And regarding this question, you have very small device, and that is not unusual. We all have really small devices. We have smart watches, we have all the things, and they still have some cellular connection, for example, right? That's lower frequencies. So usually what we try to do is we try to use as much free space as possible. For example, don't use like antenna, like for example, printed antenna that will take half of your PCB. Maybe try to use some 3D shape. So to use your like enclosure as an like and print antenna there. For example, using some like LTS technology or something like that. So or use some flex antenna that can go like up over your PCB, right, and still have the size of the PCB as a ground plane. So we kind of try in these cases. We usually try to think outside of the box. So we try to maybe integrate some like surrounding space for antenna. For example, in smartwatches, I work with one project. We use a metal element like a ring around the screen as an antenna.
All right. Next question from Ashish. What is the impact of the factor of safety on antenna failure, and is there any correlation between FOS and RF performance? So, Sifiso, can you take this question?
Yeah, sure. So the direct answer is FOS is really a mechanical property. It's a stress metric, basically, and it does not affect RF performance directly. But having said that, for antennas or any other, product, that's integrated in an electronic product, there are different, stress tests that would be done on that. And they range from shock and vibration. If you're going to, reflow solder an antenna component, an FR4 component on a PCB, you need to make sure that that solder joint is strong enough. So, the antenna will undergo shock and vibration, temperature testing also, because most electronics will work in the region of minus 40 degrees Celsius to 85 degrees, right? And then seeing if, the antenna is able to withstand those sort of temperatures. And for epoxy glass, FR4, that's usually not even a problem. And then you've got drop tests as well, right? And these are all standards, industry standards, that are used for that. You got IEC standard, you got the JDEC standard as well. So that's how it typically works. So no, FOS is not something that is considered really for antennas.
All right. Now, Katerina, I think you picked a couple more questions. Can you read out the question?
Yeah. So one question about wearable devices. So how to isolate the antenna from the body? And that's a really good question. And we really struggle with that with the wearable devices because body is so loosey, like substance, right? It absorbs and reflects on different frequency, but behaves differently. A lot of radiation, and we lose a lot of efficiency when we place our antenna, our wireless device on the body. For example, like smartwatch, or if we hold phone near our head. So we need to design our antenna already in mind that we will use it on the body. So it doesn't work if we just design some antenna in free space and we just assume that then later it will work somehow on the human body. So what we usually do in this case, we maybe try to use this type of antenna that will already have some radiation in our helpful direction, right? For example, in some smartwatch, we don't need radiation towards our hand. We need radiation outside, right? So maybe we want to use some like over-the-ground type of antennas that will already not radiate even in that direction, and will kind of radiate radiation that we want to use, like effective radiation, right? Or as I said, we can use some like smart ways to place antenna in the cover or like in 3D space to maximize the like ground plane size and maybe to decrease the effect on the body. Because with the wearable devices, we also need to pass, for example, SAR certification, right? Specific absorption rate. We cannot have so much radiation going into the body. So, and that's also one of the limitations that we have. We need to, and that's why it's also good with these antennas that don't already kind of from the start radiate towards the body, because we decrease the SAR values there.
All right. And then we have another question here. I've noticed different results when using time domain and frequency domain solvers in CST Microwave Studio, particularly in radiation patterns and S parameters. What causes this discrepancy? So, Sifiso?
Yeah, we've encountered this in the past. And if we're talking about CST, for instance, CST Microwave Studio, the idea is, if you set up the simulations correctly, respectively, you should get more or less, similar results, as an example. So meshing does matter. The number of mesh cells that you use do matter when it comes to the results that you're going to get in the end. But, if we're to talk about, time domain and frequency domain, the way I would sort of differentiate these two solvers, for the time domain, you're literally looking at broadband antennas. It's a lot faster to simulate, and it's usually, quite accurate as long as you use, the correct number of mesh cells and the correct solver, like hexahedral as an example, because you don't need to have very tight meshing, unlike hexahedral TLM, which requires very tight meshing. And you need to define that meshing by yourself. And that takes a lot of experience to do, as an example. So you could use hexahedral and hexahedral TLM, but with different mesh settings, you get different results. And then also with the frequency domain solver, just make sure that, your meshing is adequate for both. And you should probably get the same results. But yes, again, frequency domain is more used in narrow band antennas, than wideband. So, if you're doing cellular, stay away from frequency domain, rather, do that for Wi-Fi or GPS or really narrow bands.
All right. We're almost out of time, so we'll probably take the last two questions. For those questions that we're not able to cover today, we will send you a summary of the Q&A via email after the webinar. So, Katerina, I think there were a couple more. Can you pick at least the last
one question about installing a device on a metal, for example, metal pole or metal plane, and how do you approach the tuning of that antenna? So this is exactly what we covered about the environment of the antenna. What I would do in this case, because this metal pole or metal plane will affect the radiation pattern a lot, because especially if you have omnidirectional antenna, right? So there will be reflection, and how they will work with the antenna, we kind of don't know without proper simulation or proper testing. So I would always include that in the simulation if you do some simulation in some tools. Then when you do in your prototyping, like when I worked with some user electronics, and I had such device that's supposed to go like on concrete or on the metal or even on the ground. That's what I did in the lab. I put like some bucket with the ground and put antenna there or device there and checked it in with my VNA or like in the anechoic chamber. Or if I needed to like metal pole, I put device on a metal pole, and that's how I tune it, and that's how I test it, because that's how it will work.
All right.
Yeah, that's a good observation.
Sorry, go ahead, Sifiso. Did you want to add something?
No, that's a very good observation, Katerina. I am old school, and there's no amount of simulation that's going to simulate real life, right? And wherever you can, you gotta mock up those things in the lab and measure them directly. And I couldn't agree with you more.
Okay,
absolutely.
So I think. Thank you so much, Sifiso and Katerina. We have several more questions, and I apologize because we're almost out of time. So just to wrap up, just a quick note on who we are at Ignion. Our mission is to simplify RF so that you, our audience, can focus on what matters the most, building ideas that can change the world. Ignion's SMD components support any radio, any band, any device. You just have to design once, you can deploy globally, and you can stay ready for future radio updates. With Ignion, what we showed you earlier, you can get immediate performance feedback, and with the virtual antenna technology, you can reach up to 95% first pass certification, saving you time and reducing risks. Plus, with up to 70% efficiency, this technology was built to help extend battery life and boost performance, even for your ultra compact devices. This came up several times today. Now, why is it called virtual? It's simply because the antenna booster, it's not non-resonant. The final resonance is shaped virtually through the PCB layout and matching network, so it turns the entire ground plane into the radiating element. You may check out the resources section of our website, ignion.io, for more useful information. We also encourage you to check out Oxion, our AI-powered antenna integration platform at oxion.ai. And you may sign up for free to our Virtual Antenna Academy. So this is a comprehensive course that will help you understand better our virtual antenna solution. So again, thank you to all of you who have joined today's session. Katerina, Sifiso, any final words for our audience?
Thank you very much. Very, very good questions. I really appreciate your asking and spending time with us.
And Sifiso?
Yeah, no, thank you. Thank you. It's been a pleasure. We'll answer some of those questions offline that we couldn't cover in this session. And again, thanks everybody for attending.
All right. So thanks again, everyone, and we will see you in our future webinars. Goodbye.
Bye-bye.
Bye.